Thanks. Yeah, right. It's a sort of review. Some things we have already seen, and some things come from this paper that you have seen online. So the paper is, you have seen it's over 30 pages. It has a lot of things in it. It's quite dense in math. So we are not going to, I'm not going to present everything that is in the paper. I'm going to do a kind of merge with some things that we have seen already, some things that we have not seen already, that are like the basis, the fundamentals for doing optimizations of algorithms on matrix manifolds. And especially from the paper, we look at BFGS, the Riemannian version of BFGS, and the application in, of this method in image segmentation problems. So yeah, so the main contributions of this paper are convergence and convergence, so convergence results and convergence rates of BFGS and of BFGS for in its Riemannian version, and the same thing. So convergence and convergence rates for the Fletcher-Reeves nonlinear conjugate gradient algorithms that we are not going to see in this talk. And then they have numerical applications in, as I said, image segmentation, and also in the space of truss shape deformations. So yeah, so and this is what we are going to see. So some fundamentals for doing optimization on manifolds, the Riemannian version of BFGS, and application to image segmentation. Okay, so we start with a more general framework. So optimization problems on matrix manifolds, they read in general like this. So the optimization problems setting is this one. So we want to minimize an objective function, which is defined from the manifold to R, with the constraint that the optimization variable belongs to, is on the manifold, okay? Is on some matrix manifold. So matrix manifolds, matrix manifold is any manifold that is constructed from the Euclidean space. In this case, we consider R n times P, okay? By taking either embedded submanifolds or quotient manifolds. So some examples of embedded submanifolds, there is the Stiefel manifold that we have already, the orthogonal Stiefel manifold that we have already seen in the previous talk. And it's going again to be, let's say, our running example in this talk. And there are also many other examples. Maybe, I don't know, later in other talks, maybe we will see the manifold of fixed rank matrices. For example, and for the quotient manifold, the most important instance is the Grassmann manifold, which maybe we will also see in some other talk in the future. Okay, so why do we consider this kind of optimization problems? The reason is that, so in classical optimization, if you want to solve, let's say, a similar problem like this, so you have all methods to treat constrained optimization problems, like you use Lagrangians, etc. In this case, what we do in optimization problems on matrix manifolds, we exploit the underlying geometric structure of the problem. So the geometric structure, so the manifold, the geometric structure of the manifold. And in this way, we can take into account the constraints, so the fact that the optimization variable belongs to the manifold explicitly. Okay, so it's and this also usually leads to more efficient algorithms. So we both have a structure, the geometric structure that we take into account, and this gives us some more efficiency. Okay, so the main references for this first part are these books. Okay, so like more or less every 10 years there is a major like a major reference that supersedes the previous one. So now usually I make before I was making reference to this book, and now since this is the newest one, so usually I look into this book, and all the three are available online. So you will have the link also in the PDF version of the slides. So okay, so now let's say I will try to go a bit faster in the first part because some things we have already seen. So like for example, in about the Stiefel manifold, we have already seen that it is a set of matrices with orthonormal columns. So this is a kind of recap. We have seen that we have a formulation of the tangent space to M at X. So in general, is the set of all tangent vectors to a manifold at X. And for the Stiefel manifold, we can have this specific form of the tangent vectors. So we have at an orthonormal matrix X, any tangent vector has this form. So it's X times omega, a skew-symmetric matrix of size P, plus X perp times K, where X perp is an orthonormal matrix such that the span of its column, so the subspace spanned by its column, is equal to the orthogonal complement to the subspace spanned by the columns of X, okay? And then K is a matrix on which we have no specific constraint apart from its size, of course. Okay, so with this format, it's very easy to compute the dimension of the manifold, and this we have already seen. So in the end, the matrices, they are n by p, but in the end, the dimension of the manifold is less. Okay, so the degrees of freedom are less than n times p, because there is some kind of geometric constraint inside. Okay. So as we have seen last time too, a manifold, a Riemannian manifold, strictly speaking, is a manifold with a smoothly varying inner product on it, okay, which is called Riemannian metric. Yeah, classically is denoted by G, but we have many other notations. So for the Stiefel manifold, we have seen the two matrix, the two possible choices. So the embedded metric, which is inherited inherited by the Stiefel manifold from the embedding space, R n times P. So it's just an inner product for matrices, which is also called the Frobenius inner product because it induces the Frobenius norm. And the canonical metric is given by seeing the Stiefel manifold as a quotient of the orthogonal group. So we quotient out all the orthonormal matrices of size n minus p. Okay, and then we have this metric, this inner product, which differs from the embedded one only for the presence of this term in yellow. And we have seen last time that, so if we want to compute the length of a tangent vector, so a tangent vector that has that format that we have seen, yeah, the only difference in the actual calculations is the appearance of this 1/2 factor here. And last time I wanted, and I forgot to put a concrete example. So for example, for p equal to 3, a skew-symmetric matrix looks like this. So where A, B, C are just some reals. So the lower triangular part is just minus the upper triangular part. Okay, and then if you do the calculations of the Frobenius norm squared of this matrix, so this part here, you have this expression. So if you use the embedded metric, you count each coefficient twice. And if you use the canonical metric, actually you divide by 2, so it is counted only once. Okay, so that's the reason why is, as I was saying last time, 2 is kind of more natural choice. Let's say it really considers the fact that there is some kind of constraint, so the degrees of freedoms are less than n times p. Okay. Okay. Um, okay, so I think that we use in optimization algorithms something that we need is to compute the gradient. In this case, the Riemannian gradient. So, I mean, you have for sure seen classical optimization algorithms in Euclidean space, in flat space, or also maybe also at the note that I sent you if you had a look at it. So if you want to use some first order information about the cost function, like in steepest descent or gradient method, another name for the same method, we compute the gradient. So okay, let f be the objective function on a manifold in an optimization problem, like defined in the second slide. And for any embedded submanifold, like the Stiefel manifold is an embedded submanifold, the Riemannian gradient is just given by the projection of the Euclidean gradient onto the tangent space at x. So for the Stiefel manifold, the orthogonal, it's an orthogonal projection. So for the Stiefel manifold, the orthogonal projection of any matrix, a generic matrix belonging to the embedding space, so a generic matrix M of size n times p on the tangent space is given by this expression. Okay, so you see it repeats like the form of the tangent vector, right? Because here we have x. It multiplies by a skew-symmetric matrix. This is an operator that gives you the skew-symmetric part of this matrix. And then we have the part in the orthogonal complement. This is a orthogonal projector and that matrix. Okay. Yeah, and as I said, nabla f of x. So the gradient of f of x is the Euclidean gradient of f of x. So for example, if you have a matrix function like this one, so this was the function coming from that talk that I gave on federated learning. So this is the KPCA objective function. Yeah. Okay, but here we just look at it as a matrix function of x with some matrix A. If you compute the Euclidean gradient, this is just minus A times x. And then you plug this, you insert this into this, and you use the expression for the projector, and you have the Riemannian gradient on the Stiefel manifold for that objective function. Other tools that fundamental tools in Riemannian geometry and used in optimization, or at least in some approximate version, are the Riemannian exponential and logarithm. So this we have also seen last time. So if we have a point on a manifold and a tangent vector to the manifold at x, and gamma t, the geodesic emanating from that point in the direction of psi. So the exponential mapping is the mapping from the tangent space to M, such that it maps the tangent vector to the point on the geodesic at t equal to 1. So where t is the parameter is the real that parameterized the geodesic. Yeah, and then of course, if t is not equal to 1, so this, I think it feels kind of natural. If it's just a generic t, and we map a scaled version of that tangent vector psi, we just get gamma t. Okay. And then it's possible also to define the inverse mapping of the exponential that is called the logarithm mapping. And okay, so we have already seen that in some cases we have both explicit expressions for both these two mappings. So like in the case of the sphere, which is depicted here, we have explicit expression both for the exponential mapping and for the Riemannian logarithm. Which is not always the case, as we have seen last time for the Stiefel manifold. Yeah, so here we also have a slide on the Stiefel manifold. Again, as I said, so we have the explicit expression with a canonical metric. It has this form. So as I said, we just choose a t equal to 1. And then this is the expression of the Riemannian exponential. So there is the base point and the tangent vector involved, as we expect. Okay. This is the matrix exponential, and yeah, okay. So this we have seen, and this is what we have seen last time. So there is no explicit expression for the Riemannian logarithm on the Stiefel manifold. Okay, another thing is the distance. Another tool, another object. It is defined. So the most general definition is as a it goes through the length functional. Okay, so we first define a length functional of a curve. Here it doesn't need to be a geodesic. It's just some gamma is just some parameterized curve on a manifold. Okay, it's just some curve on a manifold, and then we compute this integral. So this just gives you the length, okay, of a curve. This is the Riemannian metric. As I said, sometimes we use G to denote the Riemannian metric. Well, usually we use G, but in matrix algorithm we use other things. So it is the Riemannian metric, and this is the derivative of the curve with respect to t. Okay, so this gives you the length. And then the distance is defined as the minimum of over all the curve that connect. So the distance between 2 points is defined as the minimum over all the curves that connect these two points. Okay, so it will be, it's really the minimal distance. Okay, so yeah, like that is the distance. Yeah, and then from the practical point of view, so this is the general definition. From the practical point of view, what we do on matrix manifold is that if we are given 2 points and xi such that it maps to the second point, then the distance equals the length of the tangent vector let's say the tangent vector which gives the direction of the curve of the geodesic. And so we can just compute the distance between 2 points as the norm of the tangent vector with some metric, with some inner product that we choose. And we have seen that this is equivalent to computing the length of the Riemannian logarithm of y with base point x, because the Riemannian logarithm will give the tangent vector psi. Okay. But this is just a recap. It's not what we need in this type of problems treated in this paper. Yeah, this is let's say the first framework for optimization algorithms on manifolds. And so, as usual, we start from their Euclidean counterparts, and then we generalize to manifolds. Okay, so recall, for example, from the notes that I sent you, that line search methods in Rn are based on this update formula. So the new iterate is given by the previous iterate plus alpha k times pk, where alpha k is the step size or step length, is just a real scalar, greater than 0. So positive, and pk is a vector in Rn, which is called search direction. Okay, it really gives the direction of search to look for a minimum. Okay, usually in optimization problems, most of the time we consider minimizing a function, I think, but okay, so I will let's say I will speak interchangeably of minimizing and optimizing in the sense of minimizing, okay, with that meaning. But of course, we can also do maximizing. So on nonlinear manifolds, how will this generalize? So pk will be a tangent vector to M at xk. In the sense, given a current iterate xk, we on the manifold, we expand the tangent space we consider the tangent space at M at x to M, okay? And pk will be a tangent vector in this tangent space. And then this gives the direction of the curve. And then we search along this curve in M, okay, whose tangent vector at alpha equal to 0 is pk. So this leads us to the concept of retraction because, I mean, let's say one might ask, okay, which curve, which kind of curve? Does it always need to be a geodesic curve, or can it be also something else? Okay, so this leads us to the concept of retraction. So retractions are mappings, are smooth mappings that allow us to move in the direction of a tangent vector while remaining constrained to the manifold. So it's really like this picture, okay? So there is a curve that is emanating from x in the direction of psi. But yeah, we have to stay on the manifold, so we have to remain constrained to the manifold. And then there are some local conditions that preserve the gradients at the point x. We will see in the next slide. So the Riemannian exponential mapping that we have seen before in this talk and previous talk is also a retraction. So because of course it allows us to remain constrained to the manifold, right? Because it maps from the tangent space to the manifold. But from the point of view of numerical algorithms, it's not computationally efficient in general, especially if you start to have big problems, okay? This is because of the way the matrix exponential, which is usually involved, is implemented maybe in the numerical algorithms. And also another thing is that in the numerical algorithms, in the end, we are looking for an approximate solution, not the exact solution to the problem in any case. Well, it will be very close to the exact solution if our tolerance is really small. But so what I mean is that, okay, it doesn't make sense to use the best possible thing that we have. So in this case, the Riemannian exponential, if all the rest is already approximate and we are looking for an approximate solution, right? So it's better to also maybe look for an approximate version of this that is more efficient, that is easier to compute and more efficient. So that's what retractions are. Retractions are in general first order approximations to the Riemannian exponential. So really like doing a Taylor expansion, a Taylor series, and then you truncate it to the first order, and this might give you a retraction, okay? Okay. Do you have any questions? Or we can postpone at the end also, as you want. Yeah, so also these tools have been around for quite some time, and yeah, so this is a good paper which explains how to construct retractions in general. Okay, so some more mathematical details about retractions. So properties that we ask a retraction mapping to satisfy is the fact that, so the retraction at x of 0x denotes the 0 element in the tangent space. So it is an element, tangent space is a vector space. It has a linear structure, right? And that's why we are interested every time to go through the tangent space, because in the tangent space, it's flat. We know how to do things because, yeah, we know how to do things in Euclidean space. So the retraction at x of 0x is equal to x. Well, so if you think like psi, like 0, and then we map to the retraction, well, it's equal to x, no? This is natural. I mean, we don't want to get another point on the manifold. And then with the identification of the tangent space at 0x to the tangent space at x to the manifold is identified with the tangent space itself. So let me explain a bit this. So a tangent space at x to m is also a manifold. It is a linear manifold. the Euclidean space is a manifold. It's flat. It just doesn't have any curvature, so we can still consider a tangent space to that manifold. Okay, but this is identified as the tangent space itself to M at X. Okay, so with this identification, Rx, the retraction, satisfies this condition which is called local rigidity condition, such that the differential of the retraction at the zero element of the tangent space is equal to the identity mapping on the tangent space. So why do we ask for this property? The fact is that in the optimization algorithm, we will have also involved the derivative of the retraction. So, well, we will, yeah. And the reason is that, okay, so maybe let me just explain the two main purposes and then I go back to this. I think it will be clear. So the two main purposes of the retraction is to turn points on the tangent space to points on the manifold. Okay, this just said, because we always want to be constrained to the manifold. And the other thing, so really in the optimization algorithm, we want to transform cost functions, objective functions that are defined on the manifold in a neighborhood of X, usually so locally, okay, in a neighborhood of X, point on the manifold, into cost functions that are defined on the tangent space. It will also be in a neighborhood. Okay, it will not be maybe on the whole tangent space, but okay. So the cost function, which is sometimes called the lifted cost function, because it is lifted up to the tangent space from the manifold to the tangent space, is a composition of the original cost function with the retraction. Okay, so the retraction goes from the tangent space to the manifold, and this function goes to the manifold from the manifold to R. So the composite function will go from the tangent space to R. Okay, so now this function it's really nice for us because it goes from a Euclidean space, which is the tangent space, to R. Okay, so this brings us back, let's say, to the Euclidean setting in a certain sense. Okay, at least locally in the tangent space. Okay, so that's the reason why we ask for this local rigidity condition. Okay, because it means that at X, okay, so zero element on that tangent space, we will have a kind of we have a kind of coherence given by the identity matrix. Okay, at that point when we take differentials of this composite function. Okay. Yeah, there will be some formulas afterwards in the context of BFGS about the differential of this composite function. Yeah, so specifically for embedded submanifolds, the retractions, so okay, maybe, let me just say, so there is a general recipe for constructing a retraction on embedded submanifold. And this is due to the fact that, the manifold is embedded in Euclidean space. So when we are on the tangent space, an element of the tangent space can be seen also as an element of the embedding space. So it's, so with some, let's say, a little abuse of notation, we can write that if we sum X, a point of the manifold, plus a tangent vector, we are in the Euclidean space, the embedding space, calligraphic E. So the recipe is like this. So we move along psi to get to X plus psi in the embedding space. And then we map this element, X plus psi, back to the manifold. For matrix manifolds, we use matrix decompositions. So for the sphere, for example, this is really easy for the unit hypersphere because we just apply this recipe. So we move along psi to get to X plus psi. And then for the sphere, just a normalization, right? So we divide by the norm of this vector, and this will give an element of the unit sphere, because it will be a vector with unitary norm. So this is really easy for the unit sphere. For the Stiefel manifold, as I said, usually retractions are based on matrix decompositions. So given a generic matrix in the embedding space, so in that calligraphic E, in this case, a matrix n times p, of size n times p, and of full rank. This is the notation of this is notation often used in numerical analysis for full rank matrices. We have two main matrix decompositions that are used. The polar decomposition, which reminds, it has this name because it reminds us of the polar form of the complex number. So with the radius and so rho e at the power of I theta, with the radius and theta the angle. Okay, so the generic matrix A can be decomposed by U times P, where U is an element of the Stiefel manifold. So in a certain sense is the part that is the rotation, let's say. So like the theta in the polar form of the complex number. And P, it's like analogous of the radius, the rho in the polar form of the complex number. So it is a positive definite symmetric matrix. Okay. And the QR factorization, which is basically the Gram-Schmidt algorithm for orthonormalization, which gives us the form of Q for A, Q times R, with Q, again, an element of the Stiefel manifold, which is what we want, and R is an upper triangular matrix with positive diagonal elements. Okay, but these are details, and details that we look when we implement them, of course, important, but I just want to give you an idea. So for the Stiefel manifold, the retraction based on the polar decomposition looks like this. So there is a part which is x plus xi. So again, like from the point x, we move in the direction of the tangent vector, so we get x plus xi, like in the sphere, exactly the same. And this part, this matrix, which is the inverse of the square root of the matrix square root of this part. It's like the normalization factor, if you want, right? Because it really looks like the expression for the sphere, right? So we have x plus psi and then a normalization factor. So here is a scalar. Here, of course, is a matrix. But, I mean, the meaning is there is an analogy, okay? So the meaning is the same. And the other one, so the retraction based on the QR factorization. Similarly, we do x plus xi, and then we do the QR factorization, but in the end, we are interested into only the Q factor, so the part that is on the Stiefel manifold. So let's say we neglect the R, and we keep the Q. So this notation QF, this stands for Q factor. QF, and so okay, so we don't care about the R factor. We just keep the Q. Okay, so now that we have these retractions, we can build a line search method on a manifold. So in general, they use this update formula. So where the new iterate is given by the retraction at xk of alpha k pk. Okay, so the retraction maps this alpha k pk, which is a tangent vector scaled by alpha k, back to the manifold. And so every iteration update looks like this. So the method, let's say from a high level, it will look like this. So we choose the line search method. So we choose a retraction R Rxk. Well, usually it stays the same for the whole algorithm, but it might also change at every iteration, actually. So we choose a retraction we select a search direction, pk, in some way. We are going to see this. And we select a step length, alpha k. This, we are not going to see this because we would need like a talk only on line search strategies. So yeah, we select a step length with some conditions, like Armijo condition, Wolfe condition, Golsing condition. So there are many things. Yeah, so let's say we have a way to select the step length. Okay. Yeah, and regarding the search direction, so if we choose the search direction as the anti-gradient, so the negative Riemannian gradient of f at xk, we get the Riemannian steepest descent. So the Riemannian counterpart of steepest descent method or gradient method. Some people call it gradient method, some people call it steepest descent. Personally, I prefer steepest descent because it gives already two informations about how this method is. Descent, because it considers a descent direction, a direction in which the function is decreasing, the objective function decreases, and steepest because it considers the direction for which this decrease is the optimal one, the maximal one. Yeah. Instead, if you say gradient method, I mean, yeah, it might be okay. Well, what does that mean? There are also some other methods that are called gradient method, which are not in optimization. So I prefer this term. But in the paper, I think they call it gradient method, if I remember well. Yeah, and this is the formal algorithm that is also in the paper of Ring and Wirth. It is stated like this. So, okay, this is just a repetition, but I mean, the pseudocode of the algorithm. It looks like this. So you see that, so yeah, so you see where this update formula enters in, and yeah, so. And as I said, if we choose other directions, we get other methods. So if we choose the anti-gradient, we get the steepest descent method. If we choose other directions, like we will see later, we can get, for example, a Newton method or a quasi-Newton method. But the framework is always this algorithm for this kind of methods, for these line search methods. Yeah. Okay, and another tool that is important for BFGS, in particular for this talk, is the parallel transport. We have seen this. I mean, yeah, when I gave a presentation, even if it was like 2 or 3 months ago, about the federated learning on Riemannian manifolds. So let me just also recall a bit. So given a Riemannian manifold and 2 points on it, the parallel transport is a linear operator that preserves the inner product. Okay. Let's state it like this, then I will give some more details. So here you have the specific case of a sphere, so you can fix your ideas on this illustration. So you have 2 points, x and y. You have the tangent space to the sphere at both the points, okay? And you have, let's say our starting point is x, and you have 2 tangent vector here, psi and zeta. So the parallel transport allows us to transport these 2 vectors in a parallel way, let's say, that's why the name, to transport them to the tangent space to M, to the sphere at Y, in such a way that the parallel transported psi and the parallel transported zeta, when we compute their inner product, gives the same inner product, the same result that we had at x. This is a very desirable property. And the question, so which is also like a problem question in general. So how do we transport this? Because we need a curve. We need a curve to transport these vectors, these tangent vectors to the other point. So yeah, so in general, computing the parallel transports require numerically solving ODEs. Why? Because because it is defined on for geodesics, okay, for gamma geodesics. We have, I didn't recall here, but last time we saw that, like for example, for the Stiefel manifold, we have a differential equation to solve for the geodesic. Then in the specific case of the Stiefel manifold, we have already the explicit solution. But okay, let's say in general, we have an ODE to solve to find the geodesic. Yeah, this is because of the definition of the geodesic also. So in general, we should solve an ODE numerically. And yeah, so if we choose the minimizing geodesic as a curve to move from x to y, we need to be able to solve, to compute the Riemannian logarithm, okay? And we have seen that it's not something easy to compute, and we do not really need that because, as I said, in the numerical algorithm already everything is approximate. So, okay, let's not just use something that is very expensive in practice. So, yeah, I'm saying this so that we will have alternatives to this, okay, to the parallel transport. And what I described here, so this kind of parallel transport, which preserves the inner product. So this is true if we use the Levi-Civita connection. I don't talk about connections because it will take too much time. So this is, let's say, the more theoretical and general aspect. Okay, so this is for the Levi-Civita connection. And we are not going to see this, but if we use other type of connections, we get different properties, so we will not have this, but okay. Yeah. So because what we do in practice, we do not even use this parallel transport, so we use an approximation to it. Nowadays, I found, so now, because this is also something that developed like during the last decade, so now in the most recent references, these tools are called transporters. So the author of this paper, they do not use this name, but it's exactly what they do. They use an approximate version of parallel transport. As Nicolas Boumal writes in his book, the transporter is a poor man version of parallel transport. So we are really cheap, and we do not want to compute like the parallel transport. It's too expensive. So we use this tool. Again, it's a linear map that allows the transporter, like the parallel transport, is a linear map that allows to transport tangent vectors to the manifold at a certain point to another one. So like before, okay? But here we use another notation, okay? Before it was P, here is T. So it is useful, in particular for this paper, in defining a Riemannian version of the classical BFGS algorithm. Yeah, then there are some conditions, okay, the differential, so some way to create parallel transport is to consider the differentials of a retraction. So this is very well explained in the book. Yeah, okay, but let's just say that for us, that maybe we are more interested in the implementation, and we are more interested in embedded submanifolds of Euclidean space. The transporter, at the end of the day, it is just an orthogonal projection on the tangent space, okay? So it becomes really, it boils down to something very simple because like for the Stiefel manifold, we also have the explicit expression for the orthogonal projection, okay? Yeah, and okay, well, restricted to the tangent space. So of course it will not, yeah, so it's not a parallel transport, but it will do its job. Okay, so now we have, yeah, we now have everything to generalize BFGS to the Riemannian setting. And this is, okay, so far I was using also other references, both this paper, the references I showed, other things, and now it's really about the section 3.1 in the paper. So yeah, here there are also many details, both from a theoretical point of view and from the numerical implementation point of view. So I just want to give you the fundamental ideas and the really important idea of quasi-Newton methods. So BFGS is a quasi-Newton method. The fundamental idea is that instead of computing, so quasi-Newton methods, if you have read my notes, they consider a search direction in the same framework of the line search methods. Instead of considering the minus gradient, they consider a search direction in which there is an approximate Hessian involved. We still use first order information in the sense that we only use gradients of the cost function. We do not really compute exact Hessians, which is second order information. We use only first order information, but we use first order information to get some information about how the gradient changes. And this gives a kind of second order information in a certain sense. Okay, so we look at, so if you think also in like a very simple setting in R2, if you look at how the first derivative changes, well, if you look like at an incremental ratio which involves the first derivative, then you get some kind of information about the second derivative. Okay, so this is the idea used in these quasi-Newton methods. So instead of compute, and also in addition to considering an approximate Hessian, instead of computing the approximate Hessian, which is called BK, from scratch, afresh, at every iteration, we update it. So we update BK by using the newest information that we gained during the last iteration. So that's the reason why I sent you some notes, because there are really many things. So here I wanted to focus just on the tools from Riemannian geometry that allows to generalize the classical BFGS to Riemannian manifolds. So the search direction is chosen as the solution to this kind of equation. So here you have a differential. The notation is the same as before, PK, but it's not the anti-gradient. Okay, so it's the direction of the BFGS method. And BK is a symmetric bilinear operator, well, matrix. So it will be symmetric and positive definite. Okay. And is updated according to this formula. So this is the mathematical statement of this sentence. Okay. So we do not compute BK plus 1, so the approximate Hessian at iteration k plus 1 from scratch. But we use BK, the approximate Hessian at iteration k, and we update it with these formulas. Okay. Now, then we are going to see an analogy with the Euclidean setting. And we have SK is equal to alpha k pk, which is, in our case, given by the inverse retraction of xk plus 1. So this is related to what we have just seen for the general setting of line search methods, alpha k pk. And yk is the difference of the differential of the lifted cost function. So this frxk is the one that I defined before, is the composite function of the retraction and the objective function, f. Okay, so this is where we are doing the difference between first derivatives, the differentials. So this is where we are considering a first order information to get information about how, to get some kind of second order information. So here's the difference between the differentials. And then, we have the transporters involved. Because when we go to the next iterate, we are not at the same point on the manifold anymore. So we have to also to move the tangent vectors. And to move the tangent vectors, we need the transporters. Okay, so that's why we also discussed the transporters, and they also discuss in the paper. Okay, so it has a long history, let's say, this generalization of BFGS. Okay, so let's see a quick comparison with the Euclidean, the classical BFGS that you have in the notes that I sent you, and the Riemannian one. So here you have the difference between successive iterates, and here you don't have, it's the analog of the difference. So it is the inverse retraction at xk of xk plus 1. It gives you a tangent vector. It is lifted to the tangent space. And yk, it's the difference of Euclidean gradients in this case. And here is the difference of the differentials of the lifted objective function. This is the so-called second condition in the standard algorithm. And this is the second condition in the Riemannian version with transporters and inverse transporter involved. And this is the update formula for the approximate Hessian in the Euclidean case, where you have, this is the additional, these are the additional terms which constitute a rank 2 update. So this is well explained in the book of Nosodal and Wright. So it's just, this is just a vector times its transpose, so it gives a rank 1 matrix. This is the same, is a rank 1 matrix, so this as a whole is a rank 2 update. And we get the new one, and here is the formula that we just saw in the previous slide for the Riemannian setting. Okay. And we also have convergence results and convergence rates for this algorithm. Again, a lot of things, of course, for establishing convergence results and convergence rates. So I just give the results and the reference if you want to look at the details. So we have they establish convergence of BFGS to the optimal value fx star. X star is the optimum optimizer. So this is proposition 10. They establish convergence of the iterates of BFGS to x star. So you see this, it's the convergence of the iterates themselves, starting from the initial iterate x0. And then we have m and all these m, capital M, lowercase m, and mu are constants. So these two are related to the Hessian, I think, on some bound, if I remember well. And this is some other constant, positive constant, strictly between 0 and 1. But okay, so it's important. Of course, it has to be strictly less than 1. Otherwise, the bound would not make sense. And the convergence rate of BFGS is a very desirable property, because in BFGS, as I said, we use only first order information, so only information about the gradient, but the way it's built allows us to achieve superlinear convergence. Okay, this kind of definition of superlinear convergence. So it converges more than linearly. So linear convergence is the typical result for the steepest descent method in the Euclidean setting, and it also translates to the Riemannian setting, and you can find the details here. So same book, as I said, same book gives you convergence of steepest descent to a local minimizer in the iterates, so some formula like this one. And it says converges at least linearly, but okay, let's say it converges linearly. It might be more, but this we don't know. Instead, for the BFGS, we have superlinear convergence, so it's much faster. And okay, this is another comparison with another method, which is the generalization of Newton's method, which converges quadratically. Okay, and this is also in the same paper. Okay. Even if then they do not use it in the applications. Okay, in the time left, let's have a look quickly at the application. to image segmentation on the Stiefel manifold. This is the section 4.2. So let's see how to translate this problem setting into the Riemannian optimization framework. So it will become an optimization problem in the space of smooth closed curves. So we can represent a curve by two functions, E and G, from the unit interval to R in this way. Okay, so we have a starting point and then an integral from 0 to theta. So theta is must be yeah, I didn't write, but it's the parameter in the unit interval. And then, so okay, this is the formula plus some conditions. So we have condition that the curve of the curve to be closed. So C at the end is equal to the first one. So it's a closed curve, and unitary length. Okay, so this is the formula for the length of the parameterized curve. And these two conditions imply together, they imply on E and G to be orthonormal in L2 on the unit interval. Okay, so here there is some recall about inner product in L2 and induced norm. But okay, so mathematically, it means that this couple, E and G, is an element of this manifold. So we have unitary L2 norm of E and G, okay, norm of E equal to norm of G equal to 1, and they are normal, okay, and normality condition. So yeah, so they are orthonormal. And this set is exactly a Stiefel manifold in the paper they reverse the parameters. Okay, this is our usual P equal to 2. Okay, and a Stiefel manifold on L2 on the unit interval 2. Okay, I mean, in the sense that if we discretize this, it will really be something that we have already seen. Okay, because in the end, of course, we discretize these things, so it will have some dimension and some finite number. Okay, because we have to implement it in the computer. So it will not be L2 on the unit interval. It will be some finite discretization. Okay, then this was for curves of unitary length. These authors represent a general closed curve, so not of unitary length in general, by an element with this three parts, C0, rho, and the couple EG. So the couple EG is an element of the manifold, the Stiefel manifold that we just saw. And then we have C0 is like the centroid, so it's a point in R2, so it's R2. And rho is related to the length, is the length of the curve, so it's real, okay? Yeah, so the formula generalizes to this one. Okay, so we have exp of rho and C0. Okay. And then there are some small differences between, I think, the formulation of these authors and the one used in the paper of Ring and Wirth. But okay, yeah, I mean, we are not going to implement this now. So, yeah. So there is also a metric, which is given again by Sundaramurti and others. On the tangent space of curve variations. And okay, besides the details, what we can see is that there are some weights in this metric, and these are some parameters that we can adjust, and they do some experiments with these parameters to, yeah, we can see that later. And then, okay, there is a closed formula for the exponential map. So, yeah, So again, this kind of Riemannian geometry tool. Okay. Okay, so we have to define an objective function, and the objective function that we want to optimize on that space. So this will be our space, our manifold. So this is a manifold part. So there is a manifold part, real, and the centroid that belongs to R2. So this is our constraint. Okay. And what do we want to minimize? What do we want to optimize, minimize? This is the objective function. So we have a given grayscale image, U, okay, defined on a square, 0, 1, 2, R. So let's say pixels, and each pixel is a gray value. And we want to minimize this objective functional. So bracket C is notation for the curve. Okay, then we are going to write it in full. But for the moment, so we have A1, A2, just some positive scalar, and UI and UE are given gray values, and int C and xt denote the interior and exterior of the curve. So here I highlighted in. So there is no particular reason why. I highlighted U in yellow because I wanted to see where the grayscale image enters in the functional. Okay, so this is our data. So this is our data. We are given a grayscale image. Okay, and this U enters in the functional in these two positions, and the others are parameters that we decide. Because A1, A2, and UI and UE, it's our choice. So the first two terms in the functional indicate that the curve should enclose the image region where U is close to UI and far from UE. And the third term acts as a regularizer and measures the curve length. It is actually the curve length because it's the integral of it's the integral over the curve of ds, so it's the curve length, and in the next expression is replaced by the result, which is exactly exp of rho. Okay, so this expression, so as I said, we interpret the curve C as an element of this manifold. So it's R2, Cartesian R, Cartesian Stiefel manifold, and they add a term for a uniform parameterization of the curve. So here now, instead of the bracket C, we really write explicitly the parameter, let's say the elements of the curve. We have the centroid, the length, and the two functions that parameterize the curve, E and G. Okay, that couple there. And then it's the same expression as before, just we write C0 rho E and G. And we add this term. Okay, so this is the final objective functional. And for the numerical implementation, as I anticipated, E and G are discretized, of course. So they are discretized as piecewise constant functions on a uniform grid over the unit interval. And the image U is given, we also say, is a pixel values on a uniform grid. Yeah, sorry, I ran a bit later, but let's just see. So the last example. So they tried some general numerical examples on curve evolution using BFGS and also comparing with other methods. So here you see they start with a square and they find so they want to do segmentation of this image, this white image there. And so you have several steps. So this is step number 7, and this is at convergence. Okay, so there are not all the steps. So it must be some step at around 40, right? And this is the convergence of the objective functional to the optimal value, to the approximate optimal value, because they stop at 10 at the -8, okay? And this is interesting. So it's a comparison with other methods. Okay, in this talk we have seen just these two, the steepest descent method and the BFGS quasi-Newton method. And then they also consider two types of retraction. One, they call it geodesic retraction, so it's just the Riemannian exponential, because yeah, it's the retraction with the geodesic is the Riemannian exponential, and this is not. So this is the other, let's say, cheaper version. But you see that we do not have that much difference in the iteration numbers between the cheaper version and the more expensive version. But what is more striking is the difference between the number of iteration of gradient descent, of steepest descent, and BFGS. So you see, this is in the order of 1,000. So it's almost two orders of magnitude of difference. Well, at least one. So it's really much faster. BFGS. It really shows a superlinear convergence. And yeah, so I mean, it's a method they consider here. It's nice. I think it's really cool. So the experiments, they also did some experiments for different weights inside the metric that we just saw, which I report here for reference. And they show through the experiments that a larger lambda d, so the top row here, the first row, so from left to right. So the larger lambda d ensures a good curve positioning and scaling before starting the major deformations. So as you can see, this is a square. So this I think is, yeah, they are not successive iterations, but so this is a square at the beginning, and here is still a square, here is still a square, and yeah. So this does the positioning first, and the positioning and scaling first, this top row. As with a big lambda d. With a small lambda d, it's the opposite. We start the major deformation first. So from a square, it is already deformed at the subsequent iteration. So it does first the deformations, and then the positioning. Yeah. So this is the influence, the impact of these two parameters. Okay. And a last experiment is the contour segmentation of the cameraman image. Yeah, okay, so here maybe I think this figure is a bit confusing, but I didn't have time to present it better maybe because, so if you read the caption, so in the top row, the last step is 46, is the 46th iteration. But in the second row, the last image is 116. So let's say what I mean is, okay, among the three rows, it's not really a fair comparison in terms of the number of iteration, because here is 46, here is 116, and here is 250. Yeah, so okay, we are comparing a bit, but okay, and each row also has, okay, that makes sense. So it has different parameters of A1, A2, and A3. Okay, so it's just, I think it's just a visual example of how it works. Is not really for the numerics here. So it's really like a visual outcome. So you see that, for example, here you use many more iterations with respect to the previous two rows, the first and the second, but you have a good segmentation. I mean, at least visually speaking. I mean, I think that's the reason why they showed this. And yeah, and actually the norm of the gradient, so the discretized the derivative of the discretized objective function is not even that small. I mean, the tolerance of it, the stopping criterion is at 10 to the minus 2. And these are all experiments with BFGS, these three rows, and all for lambda L equal to lambda D equal to 1. So they chose that thing. So the lambda d equal to 1. So we are in this context. Okay. So we first do the major. So in these experiments, basically they first do the deformations and then the positioning. I think should be like that. Okay, so what are the few pros and contras? So the pros is, I hope convinced you that there is a lot of theory behind it. So the pro is that the theory is well understood. So there is really, so we know what we are doing in the sense, yeah, it's not just, I don't know, we apply some method and we don't know why it works. So we went from manifolds, matrix manifolds, optimization algorithms, and then we take this problem setting, we discretize, etc. So we know why it works. The contra, so for that specific example, the image segmentation, is that it cannot deal with self-intersecting curves. So yeah, as soon as they state, the authors, as soon as the curve self-intersect in these examples, they had to stop the algorithm because then probably, I mean, does not converge anymore. Okay.